This is a stochastic process model 6 Martingales, lecture 2, definition and simple examples. In the last lecture, we have covered conditional expectation of x given y and its properties, filtration f of t, t over the time, t over the 0 to infinity and its properties. Then conditional expectation of random variable x of t given that the filtration f of s and its properties. In this model, we will discuss an important property of stochastic process Martingale. The Martingale referred to a class of betting strategies popular in 18th century. The concept of Martingale in probability theory was introduced by Paul Levy, and much of the original development of the theory was done by Joseph Doe. Part of the motivation for that work was to show the impossibility of successful betting strategies. The definition of Martingale is as follows. Let omega f p be a probability space. Let t be a fixed positive number. Let the collection of filtration f of t, where t over from 0 to capital T, be a sub sigma fields of f. So the f is the sigma field, and the filtrations are the sub sigma fields of the f. And the probability space is defined in omega f and t is a fixed positive number. Using that, we got a filtration of sub sigma fields in the range 0 to capital T. If the expectation of x of t exists, for fixed t, x of t is a random variable. So if the expectation of x of t exists, or in other words, in the random variable is integrable. Also, if x of t is ft measurable, this also we discussed in the last lecture. Whenever we say the random variable is ft measurable, that means that the sigma field generated by the random variable x of t, that should be contained in f of t. If this property is satisfied by the random variable for a given filtration f of t, then we say for a given sigma field, we say x of t is ft measurable. So the second condition is x of t is ft measurable. The third condition, not only for a fixed t the expectation exists and the random variable is ft measurable, the conditional expectation, that is the expectation of x of t given the sigma field f of s, is same as the random variable x of s. The s can take the value from 0 to small t, where t can take the value from s to capital T. If these three properties are satisfied by a collection of random variables, that is stochastic process xt, then we say the stochastic process has Martingale property. So in this definition, we started with the probability space and we fix some positive integer, positive number. Using that, we create a filtration, and those filtrations are nothing but sub sigma fields of f. F is a sigma field. If you have a collection of random variables, that's a stochastic process. For fixed t, it is a random variable. So that random variable satisfies the integrable property and ft measurable property, and the conditional expectation over the sub sigma field f of s, that is nothing but the filtration. That is same as the random variable x of s. in that property is satisfied for all s and t lies between the interval 0 less than or equal to s less than t less than or equal to capital T, then we say the collection of random variable x of t or the stochastic process x of t as the Martingale property. So here this stochastic process satisfies the Martingale property in the interval 0 to capital T, because we are checking the conditional expectation in the interval 0 to capital T. Therefore, this stochastic process has a Martingale property in the interval 0 to capital T, not 0 to infinity. If that is satisfied by for all t, then we can say that random variable or that stochastic process x of t, or this stochastic process x of t has a Martingale property in the range 0 to infinity. Now we present the definition of Martingale in discrete time. A sequence of random variables, that is xn, n varies from 1, 2 and so on, of random variables has a Martingale property with respect to the filtration fn, where n is also running from, where n also takes the value from 1, 2 and so on. If for fixed n, the random variable is integrable, that is expectation exists, and also each random variable xn is fn measurable. The third condition, the conditional expectation of xn plus 1 given the filtration f of n is same as xn for every n. Then we say the random variable has the, then we say the stochastic process has the Martingale property, or the collection of random variable or the stochastic process has the Martingale property. So this is the definition corresponding to the discrete time. The previous definition is for continuous time. Equivalent definition of Martingale is as follows. A real valued adapted process x of t, where t is lies between 0 to capital T, to the filtration f of t, where t is lies between 0 to capital T, with the expectation is finite, expectation exists, is a Martingale. For instance, n of t minus lambda t for t greater than or equal to 0 with the intensity lambda with respect to the natural filtration f of t, t greater than or equal to 0 is a Martingale. Here n of t is a Poisson process. Some remarks are as follows. The Martingale property is equivalent to the conditional expectation of xn minus xm given the filtration f of m is equal to 0 for every m less than n. So the Martingale property is same as the conditional expectation with the difference of the random variable, expressing that the increments xn minus xm given the past fm as expected value 0. The Martingale is a stochastic process that on the average given the past does not grow or decrease. That is the meaning of the above expression. A Martingale is a stochastic process that on the average given the past does not grow or decrease. If it increase or if it decrease, we have a different name for that particular property. Now we are discussing it does not grow or decrease. So that is called that stochastic process is called Martingale. A Martingale has a constant mean. That means if you have a stochastic process satisfying the three conditions, hence the stochastic process has a Martingale property or the stochastic process is a Martingale, then the expectation is going to be constant. That is, expectation of xn is same as expectation of x naught for all n. Note that Markov property can also be given in terms of expectations. In other words, the expectation of xn is same as expectation of xn for all n. That is same as a martingale is thus a stochastic process being on average station. Average stationary means it has the time invariant property in average or in mean. Usually the stationarity property or the time invariant property is discussed in the distribution. But here in the martingale, it has an expectation of xn is equal to expectation of x naught for all n. Therefore, a martingale is thus a stochastic process being on average stationary. These above remarks is also valid for continuous time. While martingale concepts involves expectation, the Markov process concepts involves distribution. Whenever you discuss a stochastic process with the martingale property, it involves the conditional expectation. Whereas whenever you discuss the stochastic process with the Markov property, it involves the distribution, conditional distribution. A Markov process need not necessarily be a martingale, because the stochastic process having a Markov property, therefore it is going to be a Markov process. A stochastic process having a martingale property. Martingale concepts involves the conditional expectation, whereas the Markov property concept involves the distribution. Hence, a Markov process need not necessarily be a martingale. The martingale has a lot of applications in branching processes and finance. Now we are going to consider the few examples. Example 1. Let x1, x2 be a sequence of independent random variables with the expectation of xn is equal to 0 for all n. We are not giving the distribution of the random variables. We have said it is a sequence of random variable and all the random variables are mutually independent. And you know the expectation of the random variable is equal to 0 for all n. Now you are defining a new random variable. S naught is equal to 0 and Sn is equal to sum of first n random variables xi's for all n is equal to 1, 2 and so on. The filtration Fn is defined from the sigma field generated by the n random variables x1 to xn with the sigma algebra generated by the first n xi's. Now we are trying to compute what is the conditional expectation of Sn plus 1 given the filtration f of n. That is same as conditional expectation of, you can replace Sn plus 1 by Sn plus xn plus 1, because that is the way we defined Sn. Sn plus 1 is going to be first n plus 1 random variables. The first n random variables will be Sn. The last term will be x of n plus 1. The way we created the the way we created the filtration Fn is nothing but the sigma field generated by the first n random variables. Therefore, the Sn random variable is the Fn measure. Because each xi's are Fn measurable. Each xn is Fn measurable. The Sn is nothing but the first n random variable, xi's random variable summation. Therefore, Sn is also Fn measurable. Xn plus 1 is independent of Fn, because Fn is the information till first n xi random variables. Therefore, xn plus 1 is independent of fn. Therefore, a conditional expectation of asn plus 1 given the filtration fn, the information up to n, that is nothing but, since Sn is Fn measurable, therefore Sn is known, because you know the information till n, that means Sn is also known. Therefore Sn has to be treated as a constant. So the conditional expectation of Sn given Fn is going to be Sn. The second term, the conditional expectation of xn plus 1 given Fn. Since Fn is independent of xn plus 1, it is not, the information up to n, it is not going to affect the value of xn plus 1 or the random variable xn plus 1. Therefore, it is just, instead of conditional expectation, it is an expectation of x of n plus 1. But already we have made a expectation of n is equal to 0. Therefore, the expectation of n plus 1, it is all, for all n, expectation of n is equal to 0. Therefore, expectation of n plus x of n plus 1, this is also 0. Therefore, the conditional expectation is going to be Sn. Since you know the information up to n, the Sn is a value. So the conditional expectation of Sn plus 1 given Fn is equal to Sn. This is nothing but the Martingale property, the last condition of Martingale property in a discrete time. Whenever you want to conclude the given stochastic process is a Martingale, has a Martingale property, 3 conditions has to be checked. The first one is expectation exists. You can find out the expectation of Sn. Since expectation of xn is 0, expectation of Sn is also 0. The second condition, the Sn has to be a Fn measurable. That is also verified. The third condition, the conditional expectation has to be Sn. This is also verified. So since 3 conditions of the definition which we discussed for the discrete time satisfied, we conclude the given stochastic process Sn, the collection of or the sequence of random variables Sn, has a Martingale property. This Martingale property is with respect to the filtration Fn, because this Martingale property is with respect to this filtration. There may be a possibility this stochastic process may not have the Martingale property with respect to some other filtration. So the given stochastic process Sn has a Martingale property with respect to this filtration Fn.